Hello friends, welcome again to the tetrahedron chemistry classes. So guys, in today's class I am continuing with the water softening methods, and my today's topic is ion exchange method, which is also known as the demineralization method or the de-ionization method, right? So as I have mentioned here, this is de-ionization or say demineralization of the water sample, hard water sample. It is also known as the ion exchange method, right? So though this method is not very much suitable for the lab purposes, right? Because see, ion exchange resins are quite costly, and equipment is also again a costly one. So it's not a very good idea to deal with this when you are doing in these things in your lab actually. However, industrially, if you are doing and you want some extra pure water or water of high purity, then this method is actually quite useful. So we will see that method of ion exchange today, right? So guys, you can see these are the resins. Basically what happens in this water treatment method, we use these resins actually. So you can see if we, in this inset here, the microporous structure of gel you can very easily see, okay? And in this microporous structure, we have the exchangeable ions, right? Like cations we have in this, and anions with these anions we are also having in these. So whatever the cations and anions are present in the hard water, they will exchange with the ions present in the resins. We will see what are these resins and how actually they react with the hot water. But this is just for your information, for your knowledge, how these resins actually looks like. And remember, they are very costly ones. So this photograph I have taken through the internet, and I am acknowledging the person to which actually this photograph is this photographs belongs. And this is the packet, right? In this packet, if you open this packet, then you will find this kind of the resin. So this is the physical appearance of the resin. And again, this photograph I have taken through the internet. So again, I am acknowledging the person. So this actually looks like in that manner. So this is one column, right? And this is another column, and in this container you will have your soft water after the treatment. And here you can see in this small panel here, there would be some conductivity meter like thing. So when your water is actually completely demineralized, then it will show the conductivity of 0. So this is the rough diagram of that water softener, okay? So these are these two pictures actually I have taken through from the internet to actually give you the little idea how they look like. So now we will move to the chemistry, what chemistry is involved in it, okay? So you can see guys, this is the cross section diagram. See the diagram which you have seen earlier, this is the cross section diagram of that part. And if you see that particular diagram completely, so actually it is starting from here actually. This is known as cation exchanger column. This column actually is known as the cation exchanger column, okay? So why it is called the cation exchanger columns? Because in your water sample, whatever the cations would be present in the form of the hardness like calcium ion, magnesium ion, and any other hardness causing ion, they will be actually exchanged with the ions which are present in this cation exchange resin. And generally in the cation exchange resin, the exchangeable ion is the hydrogen ion, H positive ion. What is the meaning of that? Say I am explaining this one. See, this is your inlet for your hard water. Say your hard water is coming through here actually. So what you can do, say you are percolating your hard water droplets from here, right? From here actually, okay? And these water droplets actually are passing through the zeolite bed. So they are coming out from here, okay? So what will happen? Of course, your hard water will have the calcium ion, magnesium ion, and any other ions, and this will have actually the H positive ion. So what will happen actually? Whatever the hardness causing ion would be there in your hard water sample, they will retain by this cation exchanger, and in turn this cation exchanger will give you H positive ion to the water sample, okay? So now this water will move from here to here, okay? So what is happening here actually, the hardness causing impurities are retaining in this cation exchanger resin, and water which is coming out from here, it is having the extra H positive ions, because these H positive ions were the exchangeable ions present in the ions. Later we will see with the help of the reactions also. Now with the help of the pump, we will actually supply this water from here to here, and then this water would come in the second column, which is known as the anion exchanger column. And if you fill the resin here, then it will become the anion exchanger bed. So in this anion exchanger bed, you will have the anion exchange resin, and in this cation exchanger here, in this cation exchanger, you will have your say cation exchange resin. And gravels are also there. These gravels are nothing, they are the say medium sized smooth stones actually, and they provide the filtering aid, nothing else. They will do the filtering, nothing else. Okay. So now coming back to here, your water will flow from this column, and now it will pass from your anion exchange column. So you know, in your water sample, cations cannot retain, cannot actually there in your sample, in your water sample alone, it will also have some anions also. Say for example, your water sample is having different anions, like chloride ions it is having, okay, and similarly you can have say sulfate ions if they are having, so they are coming here. So this water which is actually coming from here, it will have extra H positive ions as well as these negatively charged ions. So in this anion exchanger column, these actually anions will retain in this anion exchange resins, and whatever the water would come from here, actually it will have OH negative ions, okay, OH negative ions, because these are the exchangeable ions which are present in your anion exchange resin. So what will happen, see, H positive you are getting from here, OH positive you are getting from your anion exchanger column. So these H positive and OH negative would combine, okay, H positive and OH negative, they will combine, and when they combine, they will form water molecules. So you can see in that manner they will form the water molecules. So you will have the extra water here, but remember, these impurities are present in the parts per million, not very high in the amount. So volume of the water will remain same, there is no difference. So when it comes from here, you will get actually your soft water, which I have written here, okay. So this is just the procedure how actually this ion exchanger columns or ion exchange resins works actually. Now these two columns I have completed. Now coming back to here at this, the extreme left here, which is known as the acid regenerator. See, as I already told you, these ion exchange resins are quite costly. So we cannot discard these resins after using only once actually. So we have to actually regenerate these resins again and again. However, 100% regeneration of these resins are not possible, but we will do that one. So you can how we can regenerate. See, when you soft your water with the help of this cation exchange resin, so after some time actually all the ions present here in the resin, actually all the H positive ions present in the resin would be exchanged, and at that time this your exchange resin actually is called exhausted resin, and it will not work again. So you have to reclaim or regenerate this resin. For this, what you will do, you will pass dilute acid through here, right. So this is the injector for the acid, and then you will pass the acid through it. So what will happen if you pass the acid from here to here? So acid will have the H positive ions, extra H positive ions in very large numbers. So all the H positive ions will now actually gain their position in the cation exchange resins, and in turn all the hardness causing ions would be come out and would be taken from here as the sludge actually. So this is how you can regenerate this one, okay. And in the right hand side column, this is anion exchanger column, which were having actually earlier OH negative ions, but after the use of that resin, it will also become exhausted. That means the OH negative ions, whatever present in these anions, would be exchanged. Now this will have the chloride ions, sulfate ions, like that. So these ions now we have to remove. So for this we will actually regenerate this anion exchanger column by passing the alkaline solution. So NaOH you can take, sodium hydroxide you will take, and this sodium hydroxide, what it will do, it will actually remove this chloride and sulfates from here, and OH negative ion will take their position in the anion exchanger resin. So this is how you can reclaim it. So the purpose of the reclaiming these resins is not, is only what, the cost efficiency, because these resins are quite costly. So this is the diagram which actually explains the working of these columns. Okay, now we'll see the reactions, what reactions are there. So whatever I have explained you, this is all written here. So what I can do, I can very quickly read this. Okay, however, this is not the way of presenting your lectures in the form of the slides, but this is I am giving you for your examination. So what you can do, you can take the snapshot of this, right, or screenshot of this, so that it will be helpful, it will become helpful for you for your examination as well. Okay, so ion exchange process, as you can see here, it is also known as the demineralization or de-ionization process. In de-ionization process, all the ions present in the water are eliminated. Whatever, if the cations or the anions, whatever they are, they will be eliminated by using the ion exchange resins. Okay, so now what are ion exchange resins? The picture I have already shown you for these resins, but chemically what they are, actually they are insoluble. They are insoluble in water and cross-linked polymers. They are cross-linked long chain organic polymers, and it will have the microporous structure, because it is necessary to have the microporous structure for these resins, because water has to percolate it from through it, through this bed actually. Okay, and so these ion exchange resins are the insoluble, water insoluble, cross-linked long chain polymers with microporous structure, and it will have the certain functional group. Okay, so what kind of functional group it can have? See, if you have here, say for example, this I have written here actually, basically resins with acidic functional groups like H positive, right, say SO3H negative, sulphonic acid, or you may have the acetic acid, but it is always better to take sulphonic acid because it is the strong one. Acetic acid is the weak acid, so we cannot functionalize that resin with that say carboxylic acid. So basically resins with acidic functional groups are capable of exchanging H positive ions. As you know, by the basic definitions of the acids, they are those substances which have the H positive ions. So acidic functional groups are capable of exchanging H positive ions with the other cations. Other cations means the cations hardness causing ions like calcium, magnesium, aluminium, whatever the soluble ions are there other than the sodium and potassium, they will be actually exchanged at the expense of the H positive ions present in the resins. Okay, and then resins with the basic functional group, they are capable of exchanging OH negative. So what you can do, you can add OH negative there. Okay, so basically these resins are of two types, cation exchange resins, and remember, cation exchange resins will remove the metal ions, and this is the anion exchange resin, it will remove the anions like chloride, sulfates, right, bicarbonates, like this. Okay, so you can see the here the structure of the resin. This is the cation exchange resin. So what this resin is actually, you can see I have written here, it is mainly styrene-divinyl benzene copolymers. Styrene molecule, you know, benzene having CH double bond CH2 over there. So I can actually draw the structure. See, this is your benzene ring. Okay, this is your benzene ring, and if this having this functionality. Okay, so this is your styrene, and you know, when you polymerize your styrene, you will get the polystyrene. So here is the polystyrene polymer. So it is mainly styrene. Divinyl polymers, that mean two types of the vinylic linkage would be there. You can see here one vinyl here, and if you take the second molecule, second vinyl here, so they will polymerize. Okay, and this will form the cross linking also. This is the cross linking which is present here. So this cross linking will provide actually the stability to the resin actually. So this is the cross linking, and you can see here SO3 negative H positive. So this H positive, these H positive which are present in the resins actually, see, when you pass water through it, so what will happen, this H positive would come out to the water sample and hardness causing ions would retain here. So this is actually what your cation exchange resins. This is the structure of the resin actually, the chemical structure. And then you can see the anion exchange resins. Again, they are the styrene-divinyl benzene copolymer type of thing. Okay, again you can see here, this is your styrene molecule, and it is forming the cross-linking to form the polymer. And here this OH negative is responsible. So this is actually what secondary methyl type of group, basic, and OH negative is there. So what will happen if you pass that water through it? So chloride, sulphate, whatever they are present in the water sample, they will retain here actually in the form of the bond, and OH negative would come to the water sample. Okay. So this is how you can understand the structure, and you know when it will become exhausted and it will not say performing activity of softening water. So you can reclaim it by passing the NaOH solution. Okay, this I have explained. So these are the reactions involved in it. So see, it is not actually possible for the student to write the giant structure of resins again and again. So in the textbook, what it is written there, they have actually simplified the reactions. So R part is actually the polymer part. Okay, and H positive, which is important, it is actually the exchangeable ion with the hardness causing ion. So what is happening here? See, when these are the reaction which are taking in the cation exchange column. So cation, this is hardness causing ion. So what will happen when you pass water through these columns? So the reaction would take place in that manner. Calcium would be retained by the polymeric part, that means resin part, and equivalent amount of H positive ions would come out to the water sample. So it is very important to remember, I am using the term equivalent. Okay, this is very significant. Why? Because calcium is 2 positive and hydrogen is 1 positive. So there is no actually straight molar relation between them, but equivalent relation is there. So whatever the calcium would be retained by the resin, equivalent amount of the hydrogen ion would be come out to the water sample. Similarly, you can do the reaction with the magnesium also. If you can do the reaction with the aluminium, you can write RH positive, then Al3 positive, then it would be actually R3 Al and 3H positive would come to the water sample. So these are the two reactions which, see, why I am showing only calcium and magnesium, because they are generally present in the hard water. Now then again, anion exchange resins, the reactions which are happening in the anion exchange column. So this is actually anion exchange resins, and earlier in the few slides back you have seen these OH negative ions are present in the resins. So these are the anions actually which are present in the water sample. Carbonate I have written, though it may be the bicarbonate also. So when it will then when chloride ion reacts with this one, so it will remove OH negative ion. That means the OH negative ion would come out to the water. Okay, and similarly for sulphate, equivalent amount of the 2H negative, they will come out to the solution. This is how you can see the reactions. And whenever, see, after passing through the cation column and then introduced to the anion exchange column, water will have the H positive and OH negative ions. They are actually coming from the cation exchange resins, they are coming from the anion exchange resins, and finally they will combine to the to form the water. But remember, these impurities are present in the very small amount, so there would be no change in the volume of the water. Okay, so this is how you can see these reactions. So this is how the reaction goes. Now next part you can see the regeneration. Okay, when the cation exchanger loses the capacity of producing the H positive ions and OH negative ions, they are said to be exhausted, and the exhausted cation exchanger is regenerated by passing it through the dilute sulfuric acid. So you can see now this was the exhausted resin, because they retained the calcium and the magnesium ions. Now you will pass actually the dilute acid through it. So when you pass the dilute acid through it in the excess amount, so what will happen? Calcium would come out, and again you will get your regenerated resin. Similarly for your basic part, you will see these anions are retained by the resins, and when you react this with the NaOH solution, so the OH would come here and it will give out sulphate ion. So this is the regenerated one, but remember 100% regeneration of these are not possible. So this is the regeneration part. Now you can see what are the merits actually. The process can be used to soften highly acidic alkaline water and alkaline water. See, you have seen your resins are having the acidic functionality as well as the alkaline functionality. So it doesn't matter whether your water is acidic or basic, you can straight away put this into actually you can straight away hard water subjected to the ion exchange method actually. While remember, you can recall in your zeolite process or in the permuted process, you cannot use highly acidic water because acid can burn the zeolite bed, but in that case you can use this. Okay, and it produces the water of very low hardness. Okay, so 2 ppm it is written here, but sometimes it is also possible you can get this extra pure water with say 0 conductivity. That means there is 0 ppm impurity would be there. So these are the advantages, and of course certain disadvantages are also there. The equipment is quite costly and more expensive chemicals. As I told you, the resins are very costly. If I correctly remember, actually I brought these resins for my lab say way back. So it's 500 gram actually was costing somewhere 1500 to 2000 rupees actually. So it's very costly actually. Okay, and moreover it will see, however 1500 to 2000 rupees is not that much high for 500 gram, but 500 gram will not solve the purpose. You need actually kilos of these resins. Okay, that's why the process is actually quite say expensive. Okay, and second disadvantage is there is if your water is actually turbid, very high turbidity particles are there in it. So what will happen, they will clog the microporous structure and the output of the process would be reduced. Okay, and when the output would be reduced, of course the actually the anion exchange resins would become exhausted by this turbidity only. Okay, so it is very important that your water must have the turbidity below 10 ppm, otherwise you have to remove that impurity with this actually coagulation or the filtration process. So right, so guys, this was all about your ion exchange resins, and you may have the questions in your semester examination from this technique also. Okay, that's it for today. In the next lecture I'll meet, or I'll come with the some other concepts on the water treatment, maybe the reverse osmosis or the other kind of thing. Thank you very much.